value. Okay, and it's obviously a joint probability, and you can also have your marginal probability as well. Okay, and then you are given certain value from this table, and you are asked, as I said, I mean, for the opposite, I shouldn't say opposite, like the conditional probability, but now it's like it's conditioned on the data. Originally, it's conditioned on the parameter. Okay, so if you feel like, well, this looks strange, don't worry, because I'm going to give you a more concrete example shortly. Okay. But before that, let me, remind you, okay, the base rule, okay, the base rule, the term, okay, the technical term we use in the base rule, okay, okay, if you know on condition of the theta, the probability of the D, okay, this term, okay, is called likelihood. And the P of theta is normally what we call prior. Okay, and this one multiplied by this one is going to be the joint probability of D and the theta, right? Based on the base rule you learned from the high school, right? And if you divide that thing with the P of D, okay, the probability of the theta, that's called evidence. Okay, that you are going to get what we call posterior. Okay? So, for P of D, this evidence, okay, it can be represented by this thing, right? It's a marginal probability, so you can use you can try to calculate like each term separately and add them up. So this is obviously a discrete case, right? This is a discrete case. That's why we use summation here. Okay, but you get an idea. Okay, so once you know the likelihood, you know the prior, and you can calculate the P of D, the evidence, then you can get your posterior. Okay, which is like the probability or distribution of the model parameter, okay, on condition of the given of the collected data, okay. So this is on the one side, okay, on the right hand side, you only see like a certain D on condition of theta. On the other side, you see theta on condition of the D. This switching is much more important than you may think. Okay. Of course, if you have the discrete case, we also have the continuous case. Okay, so if the variables are continuous, then the marginal likelihood, okay, this marginal likelihood is this one. Okay, by the way, P of D. Okay, or evidence, whatever you call it. Okay, okay, you can replace this one into the, the integral. Okay, it's going to be something like this. But of course, this d theta should go to the end of this formula. Okay, I again apologize for this sloppy notation, but you get the idea. Okay, you get the idea. So this whole thing, okay, is really not so complicated. Okay, the only thing that is difficult, okay, mathematically, is this formula. Okay, when you use the Bayesian data analysis to do inference, okay, a lot of time, okay, as I said, the likelihood and the prior are not so difficult to obtain. Actually, prior is more like a belief. It's more like a social agreeable result. Or even if you don't have that, okay, you can have a what we call vague prior. Okay, just uniform distribution, meaning you don't say if the parameter range from 0 to 1, you just say, oh, it's a uniform distribution. You don't favor any particular value for that parameter, and then just let the Bayesian inference to tell you how it should distribute it. Okay, how it should distribute. Okay, to be more like trustworthy. But so as I say, likelihood priors are not so difficult to obtain. The difficult part is the evidence, because evidence, when it comes to the continuous case, I mean, it is integral. And well, just like most of you guys have learned from like calculus, the integration, okay, of a given function, okay, is could be very complicated, right? I mean, if you want to get a closed form result, okay, I mean, for differentiation, okay, for most of the time, if I give you a function, okay, you differentiate that function based on certain variable, and you can give me like a closed form. But if I give you, a very arbitrary like a function, even though the function could be simple, but the integration could take you, could be very painful, okay, to obtain. I mean, sometimes you cannot even do it. A lot of time you cannot even do it. It's just, well, that's the nature of the mathematics, unfortunately. Okay, but so remember I told you, okay, traditional statistics was, I mean, has become very popular, like in the 1990, okay, sorry, 19th, I should say like early 20th century, okay, early 20th century. But the Bayesian data analysis wasn't get much attention, okay, wasn't getting much attention until late 20th century. Okay, why was that? The primary reason is because, okay, because Bayes' rule was there, okay, for 100 years. Okay, it's not like a Bayes' rule was just invented like in the late 20th century. No, okay, it was there for a long period of time. But it's just like when people, even for mathematicians, when they saw this formula, they feel hopeless because they couldn't get the closed form, okay, for arbitrary function. Okay, but now, okay, because we have a computer, okay, a computer especially personal computer becomes so, easy to obtain, okay, in the late 20th century, okay, so that actually push the prosperity of the Bayesian data analysis, okay. So a few terms to just to get out of the way, okay. For example, what is the independence, okay, of variables, okay. In general, when y has no influence on x, okay, then the probability of x given y, okay, is just probability of x, okay. When you condition x on y, but because y has nothing to do, it doesn't affect x in any way. So, so p x on condition of y equal to px for all values of x and y. If that's the case, then we say x and y are independent, okay? And also, okay, because px on condition of y, we know that this can be written as pxy joint probability of x and y, probability of x joint probability of x and y, divided by py. So if you put this thing here, then it tells you that, okay, the joint probability of x and y will be px times py, okay, for all values of x and y if, okay, x and y are independent, or if and only if, because these two things are, two ways, okay. So one interesting question, okay, are the eye color and the hair color independent? Remember the case, okay, we talked about, where is it? Here, this one. Is the eye color and the hair color, these two things, independent? Yes or no? Yes? Why yes? No, why no? If you want to say yes, you pretty much need to verify. Px y equal to px py. Okay, for all xy. So this, okay, if you have that, it tells you that x and y are independent. Okay, if you want to say, oh, they are not independent, then you only need one to give me one example that pxy, the joint probability of x and y, is not the multiplication of them. Okay, for example, okay, because we are Asian people, right? So we have brown eye, black hair, right? And we know the probability of the joint probability of brown eye, black hair is 0.11. So 0.11, will there be, well, the probability of the eye equal to brown multiplied by the probability of the hair is black. The first term is the marginal probability. The brown eye is 0.37. So this is 0.37. This one is black here, the margin probability is 0.18. So these two multiplied together does not equal to 0.11, right? Right? So it tells you that the eye color and the hair color are not independent. They are dependent. Okay, as for dependent by how much, that's a different issue. Okay? That's a different issue. I mean, there are certain ways to measure how much dependency two variables are. But here we just want to answer, these two variables are independent or not. Okay, you can arbitrarily, pick another joint probability to verify. Okay, I'm not saying, you just need to have one entry that doesn't satisfy this formula. And you can refute the case that, these two variables are independent. Okay? So go back to so many models assume that successive values of random variables are all sampled from the same distribution. Okay, the distribution remains the same. Now, every time you sample a value from this distribution, it does not affect this distribution. Okay, at least the distribution remains the same for the duration of your experiment. Okay, so those values are independent of each other. Okay,